Hey everyone. Now I'm going to talk about a couple of common types of random variables and their probability distributions that we will use later on to ultimately describe the uncertainty around our estimates in regression models as well as beyond. Okay, so first we want to focus on discrete random variables. So random variables where we have uh, countable finite sets of outcomes and we can basically attach probabilities to each of those outcomes. Okay, the simplest example of a discrete random variable is of course a coin flip. Right? We can define a binary random variable x based on that coin flip, which is equal to 1 if a coin lands on heads and 0 otherwise. Right? In general, any random variable that takes two distinct values is called a Bernoulli random variable. Right? Um, if we look at this Bernoulli random variable, we can first describe the underlying probability distribution. First, by looking at the probability mass function. And as I mentioned in the previous video, the probability mass function is the function that basically assigns a probability for each individual outcome of that experiment, right? So our outcome can either be 1 for heads or 0 for tails, and having heads has the probability of p, having tails has a probability of 1 minus p, and of course everything else is has a probability of 0, right? So there are just two separate outcomes, heads or tails, with the probabilities of p and 1 minus p, right? And so f of x, or the probability mass function of this Bernoulli trial, is then kind of defined for those two separate outcomes as p and 1 minus p, right? Um, we can then also specify the cumulative distribution function. And again, remember the cumulative distribution function tells us the probability of x taking as of the random variable taking a value of smaller or equal to x, right? And of course, the probability of x, which is 0, 1, being smaller than 0, is 0. The probability of x being between 0 and 1 is 1 minus p. And of course, the probability of x being larger or equal to 1 is 1. So that's the cumulative distribution function for our Bernoulli random variable. Okay. Um, as I mentioned, there are two more like basic characteristics of probability distributions that we usually want to keep in mind. One is the expected value. The expected value of this random variable is of course p. So on average, if you think about this from a frequentist perspective, the probability of getting heads in your coin flip is equal to what? If you think about it in kind of repeated, 1,000 coin flips, the relative proportion of heads is equal to the probability of p for an individual coin flip. Right? The variance of x is, as we discussed in the previous video, defined as the expectation of x minus the expectation of x squared, which if we plug in the expectation of x and the expectation of x squared, we get p minus p squared, which we can simplify to p times 1 minus p, which is always the same, or the variance is always p times 1 minus p for a Bernoulli trial, and note that this implies that the variance of a Bernoulli random variable is greatest when the probability is equal to 0.5. Alright, next let's talk about the binomial random variable and the binomial distribution. A binomial random variable is a generalization of the Bernoulli random variable. Right? So instead of a single coin flip, we consider an experiment in which the same coin is flipped independently and multiple times. A binomial random variable x records the number of successes in a total of n independent trials with success probability p. Right? So rather than having one coin flip, we have 100 coin flips or 10 coin flips, and we record the number of heads or the number of tails. Okay. It is therefore the sum of n independent and identically distributed Bernoulli trials, right? So basically, you could think of the Bernoulli random variable as a special case of the binomial distribution where the number of coin flips is just equal to 1, okay? So how do we specify the probability mass function? The probability mass function for a binomial distribution is equal to n choose k times p to the power of n choose x times the power of p times p to the power of x times 1 minus p to the power of n minus x, right? And so the underlying logic, of course, here is that for every number of successes, that's the probability p, the success probability p. For every heads, basically you multiply the success probability. For every tails, you multiply 1 minus p. So that's n minus x is the number of tails in that case, and then n choose x kind of specifies the number of possible arrangements of successes or heads and tails in the sequence of n coin flips, right? So that's the underlying logic of this binomial, or the function for the probability mass function for the binomial distribution. The cumulative distribution function is then the sum of those probability mass functions from k equals 0 to up to x, okay? And again, we have n choose k of p to the power of k times 1 minus p to the power of n minus k. So this is just summing up the probability mass function, or the individual probabilities of all events leading up to x ultimately, which gives us the probability of x being smaller or equal to small x. Okay. The expectation of any binomial distribution is just n times p, which again makes sense if you think about 10 coin flips. What's the expected value of that random variable? It's just n times the success probability, n times the probability of getting heads rather than tails. The variance is again, if we plug this into the formula for the variance, is n times p times 1 minus p. Okay. So here's a brief visualization of what this probability mass function and the cumulative distribution function looks like. Here we're looking at an example of flipping a fair coin 3 times, right? So the probability mass function is here visualized for all 4 possible outcomes, observing 0 heads, 1 head, 2 head, and 3 heads. It's a fair coin, so the success probability is 0.5, right? And we can kind of, if we plug this into the formula for the probability mass function, we get the probabilities for each of those individual events, which is around 1.2 or 0.12 for no heads, which is just, if this is a fair coin, that's just 0.5 to the power of 3. We have 0.3 38, a little bit lower than 0.4 for observing 1 head or 2 heads, and then again the same probability as 0 heads for 3 heads, essentially, right? So the point is that the probability mass function directly shows you the probability for each of those individual discrete events, since it's a discrete random variable, for each of those outcomes of your random variable. Okay. The cumulative distribution function then gives you again the probability of observing an outcome that is at least that is smaller or equal to the to a specific value, right? So observing a value that is smaller or equal to or smaller than 0 is of course 0, because you can observe fewer than 0 heads, but then the probability of observing 0 heads is equal to the probability that we observed here in the probability mass function, but then the probability of observing 1 or 0 heads essentially is the sum of these two probability masses, and that's around 0.5, a little bit less than, or between 0.5 and 0.6. The point is that this cumulative distribution function is continuously increasing. It is continuously increasing and approaching 1, since at the end, at the basically largest value of our random variable, we're basically including our entire sample space, so the probability of all individual event probabilities summed up is equal to 1. And at the lower end, we're of course at 0 because we're smaller than the lowest value of the random variable. Okay. All right. So we can use, or we can examine these probability distributions, or actually a lot of different types of probability distributions directly in R. There are other types of discrete distributions like the Poisson distribution or negative binomial distribution, which we will probably cover in the next semester, but not in this semester, for other types of discrete events like counts and things like that. If you want to kind of explore these probabilities, you can also easily explore these probabilities and simulate from these probability distributions in R. So how do you work with probability distributions in R? There's a basic structure in R that you can follow with any type of distribution that is directly implemented in R. The way these commands work is that there's a prefix and a distribution name. And that's basically those two components build the command in R to work with that distribution, right? If you want to draw random numbers from that distribution, the prefix is just R, right? So for example, if you want to take random draws from a binomial distribution, the command for that would be rbinom, right? If you know your x value and you want to know the density at that point, right? So that's basically looking up the value of the probability density function or the probability mass function, then the prefix is d and the distribution name, right? So d binom, for example. If you know x and you want to know the probability up to that point, so that's looking at the cumulative distribution function, then the prefix is p, and again that is added to the distribution name. And lastly, if you know the area, basically the probability, the cumulative probability, and you want to know the x value, then you can use the prefix q. All right. So to just give you a brief example, suppose we want to toss 2 coins 1,000 times and count the number of heads. And of course the sample space here, there for each coin toss is 4 different outcomes: heads heads, heads tail, tail head, and tail tail. And so this is we can describe this as a random variable where, as I said, we count the number of heads, which can be either 1, 0, 1, or 2. Okay. And now if we want to simulate this in R, this is a case where we want to draw random numbers from a distribution, so we use the prefix R. And this is a draw from a binomial distribution or a binomial random variable. So the command in R would be rbinom. And then there are a couple of arguments that we need to add. Here we have n, the number, basically the number of simulations, so that's 1,000. Size is equal to 2, so that's the number of coin flips that we do every time, and the success probability, which is 0.5 here. And if we execute this command, we get a vector of 1,000 results of that random variable. And we can look at the frequency table here, and then we see the relative frequency of each of those coin tosses. Okay. We can do a couple of other things. For example, we could say what is the probability to observe a 0 or a 1 or a 2 in each of those cases, and we again do this using the dbinem command, where we can basically get the probability mass or the result of the probability mass function for different values like 0, 1, and 2. Again, for a binomial distribution with two coin flips and the success probability of 0.5, and we get directly a vector of these probabilities. Or we could ask what is the probability to observe at least one head, and the way I'm computing this here is to just compute 1 minus the probability of observing 0 heads, which is equivalent to the probability of observing at least one head, and that's 1 minus, and then again p binem for the probability, the cumulative distribution function, where q is equal to 0, size is equal to 2, probability is equal to 0.5, and that probability is 0.75. And of course that's just the sum of these two individual probabilities from the probability mass function. All right, in the next video I'm going to talk about two types of continuous random variables.